Hey guys, this is the first set of notes. So we're going to start with 1-1, which focuses on measuring segments and angles. So what you'll see is you'll see the definitions. I'm going to go through them as well as draw a diagram and show you the notation you'll see for each term. So the first one is a point. So it's a location, has no size, and it's undefined. Okay. What it could look like is point P, or say point Q, and a dot, and then an R. So as you can see, right, we label it one as P, another as Q, another as R. So you'll see an uppercase letter to represent a point, okay, and then you'll see a dot or a point, right, representing that point. Now a line is an infinite number of points on a straight path that extends in two opposite directions with no end, and it has no thickness. Okay, so right, it's something that never ends. So you'll see the arrows going in both directions, right? And it has an infinite number of points on here, so there could be 100, 1,000, right, all the way to infinity points. But to label it, right, we can label it two different ways. We can label it with 2 points. So say we have point A and B on this line, they lie on this line. We can call it line AB, and that will have an arrow over it, a line with arrows going both ways. Or we can call a line by a lowercase letter. Most of the time you'll see it kind of cursive, right? So we can call it AB with the line and the arrows, or line L. Okay. The next one is a plane. So a plane is an infinite number of points and lines on a flat surface that extends without end and no thickness. Okay, so an example of a plane could be like this, but again, it goes on infinitely, right? And now, how do we label it? Well, we label it with either 3 points, so P, Q, R, right? So this could be plane PQR, or we can label it with a lowercase letter, so plane M. Okay, so again, these are just what you'll see, right, or in how you can notate a point, line, or plane. So we're going to move on to the next set of descriptions. This set of descriptions is a segment. A segment is part of a line that consists of 2 endpoints and all of the points in between them. So segments look sort of like lines, except instead of having the arrows, they have 2 strict endpoints. Okay. So we'd have C and D as our endpoints, and then there can be points all in between them. Okay, so we would call this segment CD, and it's just the CD with a line over it to represent a segment. Array is similar to a segment and a line. Array is the part of the line that consists of an endpoint, so one endpoint, and all the points that extend infinitely in one direction. So this will look, it'll have one endpoint, say E, and then I'll have a line going on forever, and we can represent it with any point from E to that infinity. Okay, so we'd call this ray EF, and that's with a line and an arrow going one way. You could also go in the opposite direction, but we're still going to label it the same way. So say this is K, and then J is a point that lies on that ray. We could call it KJ with a line in one arrow. Okay. The last one for this part is opposite rays. Opposite rays are rays with the same endpoint that extend in opposite directions. So same endpoint that extend in opposite directions. Okay, so right, say we have a point Q, then we have a ray going left and a point P on it, and then a ray going opposite direction, point R on it, right? We can say that QP, and so ray QP and ray QR are opposite rays. We have two more definitions. The next definition is an angle. An angle is formed by two rays with the same endpoint called a vertex. Same endpoint called a vertex. The rays are the angle sides. Okay, so there's two rays coming away from this vertex, and the rays represent the angle sides. Okay, so say we have a point B, right? And this would be a vertex, right? And then we have a ray going this way with point A, and then a ray going this way with point C. Okay, see AB, ray AB or BA is a ray, and then ray BC is a ray, and then them together, they are both the angle sides and they create an angle. Okay, we can represent this angle as angle B. We can call it angle B, or angle, it can be ABC. Make sure the vertex needs to be in the middle. Okay, vertex in middle. Okay, that's important when naming them. Or CBA, because vertex is still in the middle, but you can go in the opposite direction for naming it. The vertex always needs to be in the middle, though, when you're naming it. All right. The last definition is congruent, a relationship between two geometric figures when their measures are the same. Okay. It's sort of like they're equal, but we're talking about their measures and of figures, so we call it congruent. Okay, so we use the equal sign with a little tilde on top. Okay, so if I say, for example, angle A, if I want to say it's congruent to angle B, this is saying angle A is congruent to angle B, right? We can also say a segment like AB is congruent to CD, segment CD, or angle ABC is congruent to angle EFG. Okay, so something like that. That's how we write congruence, though. This is the symbol for congruent. All right, now we're going to look at lengths, okay? So this says, how can you find the length of segment CD? So we're looking for just C to D, right? Well, one way. So let's come up with two ways. So one way we can count from C to D, or we can go the opposite direction and count from D to C, right? So we should be able to count 1, 2, 3, or 1, 2, 3. So CD, the length, is equal to 3. Right, pretty easy. Now, there might be some harder numbers to work with. So another method that we use is we use the distance on a line, right? And we use absolute values to find the distance, okay? The first thing we want to go over first is the ruler postulate, though. It says that every point on a line can be paired with a unique real number, the coordinate of the point. So x, the coordinate of x, is a number that lines up with it. Same with y. So the coordinate of x would be 3, whereas the coordinate of y would be 7. Okay, just like in example 1, the coordinate of c is 1, the coordinate of d is 4. Now, we use the fact that we can call these coordinates and match them up with the unique real number, right, to solve the distance of a line. Okay, to solve the distance of a line, we find it by taking the absolute value of the difference of the point's coordinates. So x is at 3, y is at 7. Okay, so we're going to find the difference of the point's coordinates, right? So again, we can either go to x to y, or we can go to y to x. Okay. X to y, absolute value of the difference. So x is 3 minus, because difference, 7. Or we can say the absolute value of y, 7 minus 3 for x. Either way, we get the absolute value. So the first one is -4, which is +4, because the absolute value is the distance from 0. And then this one's absolute value 4, which is also +4. So you can see the distance is 4, and you can find it by taking the absolute value of the difference of the point's coordinates. So, right, what I'd like you to do is try example 2 right now. I'm going to have you pause it and try it, and then I'm going to write the answer. So make sure you pause this video now, and then I'm going to go through the solutions. So try it, then play the video. So hopefully you've tried it. So we're going to find KL, right? So the coordinate of K is 12. The coordinate of L is 16, right? You can either count from here to here, or from here to here, or we can use the absolute value. So say I want to find KL, right? K is 12 minus L is 16. So we get absolute value of -4, which is 4. You could also do LK, which would be 16 minus 12, which is also 4. Okay, so therefore, so these 3 dots just represent therefore, KL is equal to 4. That's our solution. All right, the next part of the section is the segment addition postulate. Okay, this one's important. It says if points A, B, and C are on the same line, as we see in this picture, they're all on the same line, with B between A and C, okay, so B is in between them, then AB, right, so this AB plus BC equals the full AC, right? Which makes sense. If you cut the full AC into AB and BC, you add them together, they should equal that full AC again. Okay, so let's do an example together of this. So it says points F, G, and H are collinear. Right, collinear means they are on the same line. Right, so we know we can use the segment addition postulate. It tells us if GH, so if we look G to H is equal to 16, what is FH? So we want the whole piece. Okay, now we're given GH is also equal to this right here. So this also equals GH. So if we know 16 equals GH and 2x plus 2 equals GH, that means we can set them equal to each other. So GH, right? We can set them equal to each other because 2x plus 2 equals GH and 16 equals GH. So that means they must equal each other. This allows us to solve for x, and this will allow us to solve for FG in the end. And we add 16 to this length of FG, and we get that total FH. So we get 2x, we subtract the 2 to the other side, and we get 14. Therefore, and then we divide both sides by 2. So x equals 7. Right, now, because x equals 7, we know FG is equal to 3x minus 1. We can figure out how, the length of FG. Right, all we have to do is substitute this 7 in for x. So 3 times 7 minus 1. 3 times 7 is 21 minus 1. So FG equals 20. Okay. Now, something about pictures we can see, right? It doesn't make sense, but necessarily you never go by the picture. Okay, so we know GH is 16 and FG is 20. FG looks much smaller, but never go by the picture, always go by the math. Okay, so now in order to find this full FH, we know FH is equal to FG plus GH. Right, and this is the segment addition postulate. Right, the two smaller parts equal the bigger part. So FG we said is 20, GH is 16, therefore FH is equal to 36. All right, and that's how you use the segment addition postulate. The next thing is the protractor postulate. So protractor looks like this. Normally in class I'd give you one to look at, but since we are distance learning, I don't technically have them to give to you. As you can see, they start at 0 right here, and it brings it all the way to 180 degrees, right? Which is half a circle, 180 degrees. Okay. This has given BA and a point C not on BA, a unique real number from 0 to 180 can be assigned to BC. So BA, right, this segment right here represents 0 degrees. So BA represents 0 degrees, okay? Then you can see BD is at 180 degrees. This is just saying if you put a point C in between, right, BA and BD, right, it has that ray that it creates will make a it will be a unique real number, so it will be a certain degree. Okay, it will make a certain degreed angle. Okay, so what this does is it makes this BC makes an angle here, right? That can be assigned to this. So this 60 right here that you see represents BC. BC is at 60 degrees. Okay. We can put another one here, say, make this F. So BF would be at 130 degrees. So it's that outside number. Okay. All right. Now let's do an example of how to read a protractor. All right, so this example for us says read the protractor to the right. So we're looking at this protractor over here. What is angle BEC? Okay. Show your work to support this answer. Okay. So in order to solve this, what we're going to need to do is we're going to need to figure out certain other angles to figure out our BEC. So we're looking for this angle right here. We're trying to find out this measure, okay, between those two. Right. In order to find that, we need to know AEC. Right. So we need to find out this angle right here. And we also need to know BEC. Okay. Which is what we're looking for. And we need to lastly know AEB. Okay. So if we look at our angle addition postulate, it tells us that angle AEB, right? So that's this one right here. Angle AEB plus angle BEC, so that's this first one right here, is equal to the full angle AEC. So if you broke it up, right, it looked like AEB plus BEC. So BEC is equal to that full angle AEC. Okay, so it's sort of like the segment addition postulate, right? The two smaller angles add up to make that larger angle. Okay, whereas the segment addition, the two smaller segments add up to make that larger segment. Okay, so right, we have the measure of angle AEB plus measure of angle BEC. So that little m means measure because it tells us that we're looking in degrees. Is equal to that larger angle AEC. Okay, so we can figure out AEC's angle, right? It hits right here. So that should be 105 degrees. So we know this is 105 degrees. We should be able to also find AEB, right? This one right here, because it cuts off at 47 degrees. Okay, so AEB is 47 degrees. And then the one we're looking for is BEC. Okay, so what we can do is to solve for a measure of angle BEC, sort of like it's a variable, is subtract 47 to both sides. And then we get the measure of angle BEC is equal to 105 minus 47, which is 58 degrees. So that's how we solve for an angle using angle addition postulate as well as using a protractor. All right, now this last example, I'm going to kind of skip through. It's kind of like an extra hard problem. So I'll quickly go through it. And if you want to try it on your own, you can pause it now and you'll have the solutions up. Okay, but what you need to do is use segment addition postulate. Angle addition postulate to find all the angles. And then the second thing to do is analyze the angles, knowing how the spotlight can rotate in the width of the spotlight. And then you want to assume it's centered in the diagram. Okay, so analyze angles, knowing how spotlight rotates. And the width of the spotlight. And it is centered. So if you want to try it using those helps, you can. I'll pause it now and then I'll put the solution up. So here's the solution. I wrote in the angles over here that you need to find, and the rug and the door and the table can be illuminated by the spotlight, but the spotlight cannot hit the chair. You'll miss by 7 degrees. So that would be your solution. Okay, so this is the end of the 1.1 notes, and if you have any questions, let me know on Remind or through Google Classroom.